we were trying to do applications, say, for public health. We might want to look at things like dietary choices, exercise levels, hours of sleep, all these things which can play into people's health, right? And so real life involves many random variables. So we need to be able to have a machinery that allows us to consider more than one random variable at the same time. So the beginning of that is to develop a theory for joint PMFs and joint PDFs, which would deal with, say, 2 or 3 random variables rather than at the same time, rather than just one. Okay. So first we'll consider joint PMFs for more than one discrete random variable. Okay? Okay, so recall that a random variable is a map from the sample space S to the reals. And we might have, say, on the same sample space, we might have, say, random variables x, y, and z, let's say. Okay. So, as an example, let's say we have a random variable x. We're going to roll a fair die. This is our experiment. Then, after the experiment is over, the random variable x is the result of the roll. And we can think of we could think of infinitely many random variables. We could define another random variable y, and y would be +1 if the result is even, and -1 if the result is odd. And now we want to do some math which allows us to consider both of them at the same time. Okay, so we roll a die, and what are the possible results for x? Well, x is the result of the roll, so x could be 1, 2, 3, 4, 5, 6. So those would be in these ordered pairs. The value that x takes after the experiment is over are the first element in the ordered pair. And then y would be the second element in the ordered pair. Okay, so if we rolled a 1, we rolled an odd, so y is -1. If we rolled a 2, then x is 2, and because 2 is even, the value y is +1, and so on for all the ordered pairs, right? The first entry in the ordered pair is telling you what the roll was, and the second entry is telling you whether that's an odd result or an even result. And that gives you all the possibilities for x and y listed as ordered pairs. Okay? All right, so let me ask you, what's the probability that x is equal to 3 and y is equal to 1?
0.
Right, it's 0. Because for x to be 3 and y to be 1 at the first time, you would have to roll a 3, and the result of the roll would have to be even. But 3 is not even. So that first probability is 0. What's the probability that x is equal to 3? 1 over 6, right? So in order for x to be equal to 3, you have to roll a 3 when you roll your fair die. With a fair 6-sided die, the probability of any result is 1 out of 6. Okay, what's the probability that y is equal to 1? 1 over 2, right. So in order for y to be equal to 1, you have to have rolled an even result. Well, all results are equally likely. 3 of them are odd and 3 of them are even. So 3 out of 6. What's the probability that y is equal to 4? 0, because y only takes values -1 and +1. Okay. Now, let's list let's list all the possibilities. All right? So, the probability that x takes a value x and the other random variable takes a value y is, there's a 1/6 probability that x is 1, 3, or 5 and y is equal to -1. Right? There's a 1/6 possibility that x is 2, 4, or 6 and y is equal to +1. And there's no other possibility. Is that okay? Well, that's basically our joint PMF for x and y. Right? So, you have a random variable x. It has its own PMF x. You have another discrete random variable y, which is defined on the same sample space. X and y are defined on the same sample space. So y has its own, right? So you have x and you have y. X has its own PMF. Y has its own PMF. And we have this defines a joint PMF. Right? And it takes certain values. You give it an ordered pair of x and y values, and it gives you some probability for getting that ordered pair. Is that okay? Okay, so basically, this joint PMF, the joint probability mass function of the random variables x and y, has to have these properties. Right? The probability of getting the ordered pair xy must be greater than or equal to 0. Probabilities are always non-negative. All the probabilities have to sum to 1. And we interpret the output of f sub xy. You give it an input of an ordered pair xy, and it gives you, as the output, it gives you the probability that x takes the value x and that random variable y takes the value y at the same time. Okay? So it's a generalization of, or it's an analog to the PMFs that we've already talked about. Okay, now, if I wanted the probability, I might want a probability something like this, that x can take values from 2 to 4, and y can take values from 0 to 7, or something like that, right? So x and y are taking values in, right? The ordered pairs x, y lie in the plane, the xy plane, and let's say that they're, I don't know, a whole bunch of values. And then you say, well, what's the probability that they lie within a region R? Well, what you do is you sum up the joint PMF values at all the points that lie within the region R. And that's the probability that x and xy as an ordered pair takes a value within that region R. Okay, so you imagine something like this. Okay, let's do some examples. Okay, so once again, we're going to roll a fair six-sided die. X is the result of the roll. Y takes the value +1 for an even result of the roll and -1 for an odd roll, as before. Okay. What is the probability that y is equal to 1? Okay. So we're considering what is the probability that your ordered pair xy satisfies that the second entry y is equal to 1. Right? Oh, yeah, so it should be 1 or 2. Okay, so what do? There's no restriction, so we sum over the probabilities of all of the allowed ordered pairs. Okay, so there was no restriction on x, so x should go from 1 to 6. There's restriction on y as well. Y can only be 1. So y goes from 1 to 1. Okay, if we're going to do this as a double sum. Okay? So you sum up all the probabilities from x equals 1 to 6 and y equals 1 to 1, the joint PMF, evaluated at the ordered pair xy. Okay? Well, okay, let's take care of the y sum first. That basically says that y is equal to 1. So that's the sum from 1 to 6 of the PMF evaluated at x1. And x is going from 1 to 6. Okay, well, we take x as 1, 2, 3, 4, 5, 6. So those are all the evaluations that you need to make. Now, 2, 1, 4, 1, and 6, 1 doesn't even occur, right? So those probabilities are 0. Yes?
The opposite. 2, 1, 4, 1, 6, 1 are the ones that occur because 1 is positive.
Oh. Okay, sorry, it's the opposite. I've got that wrong. Anyways, half of them drop out. The other half then give you 1, 6 plus 1, 6 plus 1, 6. And that gives you 1 half. Okay. Is that all right? Okay. Try another one. Okay, so we've got 5 white marbles and 6 black marbles. 5 white marbles and 8 black marbles in a bag. We're going to draw 2 of them, one at a time, without replacement. Okay, so that's the experiment. Okay. Let's define then 2 random variables, which will take values once the experiment is done. So the random variable x takes the value 1 if the first marble is white. Otherwise, it takes the value 0. The random variable y takes the value 1 if the second marble is white. Otherwise, it takes the value 0. So what is the PMF? Can you think about that for a minute? Okay, remember this is how we find the probabilities. Okay. So I suppose we could run through, if there are few enough possibilities for the ordered pairs, then we can run through them one at a time. Okay? So let's just be clear on what these mean. If I say the result for x and y listed as ordered pairs is 0, 0, what does that mean?
All marbles are black.
Right, you drew a black and then you drew a black. Okay. 0, 1, what does that mean? You drew a black and then you drew a white. 1, 0 means you drew a black and then the second one you drew a white. Sorry, white and then black, right? 1, 1 means you drew a white marble and then you drew a white marble. Okay. What's the PMF supposed to give me? It's supposed to give me the probability of this ordered pair, 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 and it should give me a probability of 0 for any other ordered pair that you feed into it. As an input, it should give you an output of 0 probability. Okay. So what is the probability that our result is 0, 0? Well, that's the probability of drawing a black and then drawing a black. Right? Okay. What's the probability of drawing a black first?
8 by 13.
Right? You had 8 black marbles out of 13 and you drew randomly and fairly. So that probability is 8 out of 13. Now, if you had a black and a black, the first time when you drew, you had drawing a black was 8 out of 13. Now you've removed one of the black marbles and you have 12 marbles left. So what's the probability of drawing another black?
7 by 12.
7 by 12. So, is that okay? Do we agree? That's the probability of drawing a black, and therefore that's the probability that you had x equal to 0 and y equals to 0 after the experiment. Okay. What's the probability of getting the result 0, 1 after the experiment? Well, that means drawing a black and then drawing a white. What was the probability of drawing a black first? It's 8 out of 13. We already discussed that. Now you've taken the black out. There are 12 marbles left, and 5 of them are white. So I think 8 out of 13 times 5 over 12 is the probability of drawing a black and then a white, and therefore the probability of getting this result for the random variables at the end of the experiment. Okay. What's the probability of drawing a white first? 5 over 13. There are 5 white out of 13 total at the start of the experiment. Then in the next step of the experiment, we've removed a white. So there are 4 white and 8 black, 12 total. And what's the probability then of getting a black? Oh, sorry, 5 over 13, right. Okay, what's the next one? We have 8 black left out of 12. Okay. Probability of drawing a white first? we already said was 5 out of 13. You've removed 1, so you've got 4 white out of 12. What's the probability of drawing another white? Is 4 out of 12. Okay. So I think that's then is the list of the probabilities for the various ordered pairs. Okay. Hopefully that's the reasoning we went through. Right, and as I said, the ordered pairs are few enough that we can go through each one separately and list its probabilities, right? And we sum up all these probabilities that we got in our joint PMF for x and y. Is that okay? All right. Okay. All right, so another experiment. We have a bin of 5 widgets. So we got 5 widgets in a bin. 2 of the widgets are defective. Okay, the widgets are to be tested one at a time until the defective ones are identified. Okay. So N1 is the number of tests that need to be made until the first defective one is identified. N2 is the number of additional tests that need to be made until the second defective widget is identified. So what's the joint probability mass function for N1 and N2? Okay, right. So, well, okay, so let's see. Supposing that I could get I could pick up the first one and it's a widget is defective, and then I could have one more test and pick up the second defective widget. Okay? Or the first one could be defective, and I pick up the next one, it's not defective, and then one more test gives me the defective widget. 2, 1, 3, and 1, 4. So there's one set of results, right? Okay. Well, okay. So let's say I don't get if I don't pick up the first, if I pick up the first widget and it's not defective, but I pick up I find my first defective widget as the second widget that I test, right? Then I could pick up the next defective. The next one could also be defective. Or not that one, but the one after that. Or not that one, but the one after that. And that's then, there are no more widgets to test. Okay? So there's another set of possibilities for, okay. Now, what if I pick up the first one, I test it, it's not defective. I pick up the second one, I test it, it's not defective. Now, I pick up the third one and it is defective. So I could have that the third widget and the fourth widget are defective. Or I could have that the third widget and the fifth widget are defective. Okay? Okay, what if the first, second, third, and third widgets were not defective? I'm guaranteed that there are 2 defective widgets out of the 5, then the 4th widget would test as defective, and the one after that would test as defective. Okay. So again, okay. We managed to list all of the possibilities. Right? Okay. Now, what are the, how would we work out the probabilities for this? What do you think? The same way we did the last one? Is it the same? Okay, so let's list the ordered pairs. Okay, each ordered pair is equally likely. Well, we had 5 defective widgets. These 2 could be defective, these 2, right? And right, if the defective widgets are distributed among the total widgets randomly, those 2 could be anywhere, right? So any arrangement is equally likely for the defective widgets. So each one of these is equally likely. Right?
We could apply binomial. Like if we
well,
define the probability, would we find that it is equally likely for all of it?
yeah, so each one is equally likely.
Could we use binomial?
I don't think we can use binomial because binomial changes, right?
How about we could maybe use binomial because
Oh, okay, think of it this way. I've got 5 cards, and 3 of them are white, and 2 of them are black. Now I close my eyes and I shuffle them. Then I close my eyes and I shuffle them again. Right? And I have an ordering in the cards. If it's a fair deck,
3 into 2 into 1 into 2 into 1 over 5 into 4, 5 factorial.
if it's a fair deck, then each outcome is equally likely. Right? And we can work out how many different ordered pairs there would be. It's basically this. But each of the hands of our deck is equally likely. Yes.
We can't use binomial because the probability of one of the first widget being defective is 2 by 5. And now if it is effective, the second widget's probability is 1 by 5. Probabilities are different, so we can't use binomial.
Okay, no. Okay. I guess the way to think about it is that if I have 2 symbols which are the same and 3 symbols which are the same, and I lay them out on a row, and I say that they're randomly arranged, right? So all of the rearrangements of those symbols are equally likely, right? And this is how many arrangements there are.
Calculate the probability of one of them which is not 1, 1. Like any pair that is not 1, 1. I'm slightly curious as to how we
Oh, okay. So, well, how many are there? There's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10.
10 times.
Right? So there are 10 arrangements. There are 10 ways to arrange 2 defective widgets among 5 defective widgets if we lay them in a row.
I'm asking, could you calculate the individual probability of one pair? For example, 2
Yes. Yes, there are 10 of them. So the probability of this one is 1 out of 10. Okay?
So essentially we're not finding the probability of each individual pairing, we're just seeing which pairing might occur.
Well, once we work out all the pairings that might occur, and then they're equally likely, and there are 10 of them, that implies that each individual pair
Each individual pairing's probability is not going to be 1 over 10, right?
is 1 out of 10.
It's not.
No, but for
example that we previously done without replacement, like 8 में like the mixed colored balls, for example. When you have taken one defective out, तो उससे अब अगला वाला भी it's not like independent event तो नहीं होगा because it is without replacement.
Okay. If okay, like I said, if think about this, that I have 5 white sheets of paper, and I say to you, write D on 2 of them. And then I say to you, write D on. You could write. We repeat the experiment. Write D on 2 of them. I say to someone else, write, and you can pick any 2 to write D on. Well, what are all the ways that you could do that? So now we say, well, what if you had 2 continuous random variables? They have their individual PDF, and then they have a joint PDF if they're defined on the same sample space. Okay. Okay, now, so what properties should our joint PDF have?
The probability should add to 1.
Okay, the probability densities, should be greater than or equal to 0. The double integral over the entire xy plane of the joint probability density should equal 1. And the integral over a region in the xy plane should give you the probability that the ordered pair xy lies in that region.
How will you do double integrals?
How will you do double integrals? Okay. We'll spend some time talking about double integrals. So. Okay, just let me. The probability that x and y take values within a region, remember before, with a single PDF of a single random variable, the probability that x lies between a and b is given by integrating from x equals a to x equals b. You're integrating over a region in 1 dimension, right? So now you're saying that, well, what if x and y, what if the ordered pair x, what's the probability that the ordered pair xy lies within this region R? Well, you do the double integral over the region R of the probability density. Here you go.
Is the only difference in the second rule and the third rule that our limits will be different?
Yes, and that's when you're doing double integrals. That's the thing. Working out how to get the limits is the tricky part. I'll try not to give you any integrations that are difficult, but in 2 and 3 dimensional integration, thinking about the limits takes some effort. Okay. All right, so let's do an example. Okay. X and y are continuous random variables. They have a joint PDF, which is defined by, it takes the value 3y on the region given by 0 less than or equal to x less than or equal to y less than or equal to 1, and 0 otherwise. So when I see that, I can't picture the region. Right? So I have to go through it carefully to picture the region. Okay? So okay. All right. So okay, well, let's just draw some lines and work out what this region is. Okay? Well, this is x equals 0 here, right? X equals 0 is this. Vertical axis, the y-axis. Okay, so I know something now. Y equals 1. Okay, so there's the line. Y equals 1 is that horizontal line. Okay. Let's see. So the ordered pairs should be lying somewhere in here, actually in a restriction of this region. Okay, so now x should be less than or equal to y. Okay, so let's draw the line x equals y. Okay. So this is the line x equals y, or y equals x. You right? Now, I'm told that x should be less than or equal to y. So are points in here in the region? The point, okay, if I have a point x, y here, does it satisfy that x is less than y? No. Okay. What about this point here? This point here is, okay, this point here is 1, 0. Does this satisfy that x is less than y? No. Right? So I want, this is the region that's being defined by those inequalities, right? So x is bigger than or equal to 0. X is less than or equal to y. Y is less than or equal to 1, and y is bigger than x. So that gives me this triangle. Okay. So that's, like I said, that's the hard part of the doing double integration.
So for both x and y, the limits are 0 to 1.
Well, okay. So we'll work out what the limits are in a bit. We'll do the integration. Okay. So that's the region that we're talking about. Okay. Inside that region, the probability density takes the value 3y. Right? At the point xy, which is inside the region, the PDF, the probability density, takes the value 3y. Outside that region, the probability density takes the value 0. Right? Okay. Now, integrating a PDF of a single random variable over the entire real line is supposed to give you 1. For two random variables, integrating a joint PDF over the entire plane is supposed to give you 1. Okay? So if I integrate, right? If I integrate over the entire plane, R2, area element, I'm supposed to get 1. Right? That's supposed to be one of the properties of a PDF. Okay, well, but I don't really have to integrate over that entire plane. I can just integrate over that triangle. Because outside of the triangle, I'm just integrating 0. So it's kind of, it would be a waste of time to do that. So, I don't know, let's call this, if I call this triangle R, then integrating over R should give me 1. Okay? Let's check and see if we're actually going to get that. Okay, so this is how you actually go about doing the integration. Okay? We want to break, when we have a double integral like this, we want to break it down into two integrals just like we did in Calculus 1. We want to break it down into two integrals. Okay? So we want to do an x integral first, and we want to do a y integral second, or we want to do a y integral first and an x integral second. It's up to you which one you do. But sometimes doing it one way rather than the other, one way might be easier, one way might be harder. Okay? So, how do we do this? So this is the way that I would imagine this. So one way to look at it is to say, if I'm going to do the x integral first, the picture I have in my mind is that I integrate over a strip. That strip has a thickness dy. And I integrate from the line x equals 0 to the line y equals x or x equals y. Right? That's my inner integral. Then the outer integral is done by integrating over y. I add up all the contributions from these individual infinitesimally thin strips, and that's an integration. Yeah, you can think of, right, so you can think of this as a Riemann sum, right? And then you're taking this dy becomes infinitesimal, so the summation becomes an integral. Okay? All right. So let's go through it, and if there's any question, you need to stop me and ask me. Okay? So let's say I decide to do the y integration first. Then I'm imagining that at some point, so my x is fixed, and my first integral is the integral over a thin strip like this of thickness dx. Okay? And then I need to integrate to get the contribution from all these strips. So this is how I start. No, I'm going to go in the y direction. Let's say I decide to go in the y direction first. You could do either way. If we're going on a vertical line, then we're doing the y integral first. Okay? So, the inner integral, we integrate the PDF. Inside the triangle, the PDF has a value of 3y. So that's how we have to integrate. We're doing the y integral first, let's say. So we have dy. What are the limits of the integration? We're going from this line to this line. This line is y equals x, not y equals a number. This line is y is equal to x. Right? And we're going up to, not to a number really, but to the line y is equal to 1. So that's why the limits of the integration in the inner integral are these functions of x. Y equals x to y equals 1. Is that okay? All right. And then I am going to add up the contributions from all of these integrals. Now, when I've done this, I've integrated y out. So all I'm left with is a function of x. So now I'm going to integrate from, well, this is x equals 0 up to, at this point, x is equal to 1. So the inner integral has functions in the limits, and the outer integral has constants in the limits.
And that's how the variables changes seamlessly in your integral.
Yeah, right? So we're going to do the inner integral first, and when you do the inner integral, you're holding this x constant. If you're integrating with respect to y first, you're treating x as if it's a constant. Okay? Because you're fixing this x. And then you're allowing x to vary in the outer integral. So that's how we set up this integration. Right? So like I said, that's the hard part. After that, it's mechanical, just like calculus 1. Okay? So ask any questions at this point. All right? So now, what's the integral of 3y? 3/2 y squared. Where is that supposed to be evaluated? At y equals x and y is equal to 1. Well, that then the inner integral gives me the result 3/2 minus 3/2 x squared dx. So bound, right? So you got x equals 0 to x equals 1. The integrand now is the result of the inner integration. And now you have to integrate that. So you turn your double integral into two iterated integrals. Okay? So now if you do that integration, well, you integrate and you should get 1. Okay. Is that all right? Okay. All right. What if we wanted to do it the other way? Okay. What if I said, no, I want to do the x integration first and the y integration second? Can you tell me how you would set up the integration?
X equals 0 to y equals x.
Okay, so let's see. Okay, so the integral over the region of the PDF area element, that's supposed to be equal to 1. Okay, let's see if it is. Okay, so what am I going to do? I'm going to integrate the PDF dx. There's an inner integral, and then there's an outer integral. Okay? Now, when I'm going, remember, the inner integral, you're integrating between functions. The bounds are functions. So what's this line? This is the line x is equal to 0. So, okay, that's x equals 0. What's this line? Y equals x, or x is equal to y. Right? So this is going to be x as a function, and the upper integral will be x as some function. And you're going to integrate x out and only be left with a function of y. Now, the outer integral then You're going to add up the contributions from all of these strips. So you're going from y equals 0 up to y is equal to 1. Okay. Now you've got, what's this PDF when you're inside the rectangle? 3y. Okay. So this is what the integration looks like.
We can't integrate this with respect to x.
Okay, now. Okay, so we've set it up as a nested integral, right? Let's do the inner integral first, okay? So this is equal to the integral from y equals 0 to y equals 1. Okay? Now, you're integrating with respect to x. So you're integrating over this strip. Your y is fixed, so 3y is a constant. I can pull the constant outside. 3y times, what's the integral of 1 dx? It's just x. And this x is supposed to be evaluated at x equals 0 and x equals y. That's the result of the inner integral. Right? Okay. So when I take x is equal to y, 3yx becomes 3y squared. When I take x is equal to 0, this becomes 0. So this result is 3y squared. So now I have to do one more integral. I have to integrate from y equals 0 to y equals 1. I have to integrate 3y squared dy with respect to y. Right? And that will be y cubed evaluated at 1 and at 0, which will be 1. Okay? Okay. Now let me ask you, what is the probability that y is less than or equal to 2x in this example? So, continuing with this example, well, what's the probability that y is less than or equal to 2x? Redraw this since it's gotten a bit messy. I have something that looks like this. Okay, that triangle, and okay, this is the line y equals x, or x is equal to y. This is the line y is equal to 1. Okay, that's the region over which the PDF has a non-zero. Is a non-zero function. Outside of that, it's 0. So when we integrate outside of that, we just get 0. Okay? What's the probability that y is less than or equal to 2x? Well, what's the region in the plane where y is less than or equal to 2x? Right. Let's draw the line y equals 2x. While y equals 2x, right? That's the same. Okay, y equals 2x, right? So it's steeper. This is y equals 2x, or x equals y over 2. What's this point here?
1.5.
Okay, y equals 2x, right? So if y is 1, x is a half, right? So 1/2 and 1. That's this point over here. We might need it, possibly. Okay, so we want, what's the probability that y is less than or equal to 2x? Is that over here, or is it over here? Well, let's see. Is the point 1, 1 there? Y is less than or equal to 2? Yeah? Okay. What about this point? This is the point 0, 1, right? So is that point 0, 1 in there? Is 1 less than or equal to 0? No. Okay, so it seems that this area is, yeah. Okay, so we already know that outside of the big triangle, right, there's no probability of it, right? So we're asked, what is the probability that the point xy lies in here? Okay. All right, so how would you do that? Okay. Right? So we need to integrate over all of this, right? So let's say that we wanted to, do an x integral first. So has a thickness dy. Let's say we want to do an x integral first. So we have to integrate 3y dx, and then we have to integrate from y. Okay, so what's this line here? X is equal to y over 2. Okay, y equals 2x, or x is equal to y over 2. I need to write x equals, if I'm going to do the x integral first, then x has to be written as a function of y. So x is equal to y over 2. What's this line here? That's the line x is equal to y. Okay, so you're going to do that one. Then you're going to integrate from y equals 0 to y equals 1. Remember, when you do the x integration, your y is held constant. Okay. Oh, well, if I'm adding up all of these strips, I'm going from the strip which is at y equals 0, which is up to y equals 1. Yeah. Okay. All right. So you should make sure that you can do that. Why don't I want to do the y integration first? Okay. Well, you could do the y integration first, but when you do the y integration first, if you were here, then you're going from y equals x to y equals 2x. And when you're here, you're going from y equals x to y is equal to 1. Right? So you'd have to break it up into two pieces to do that integration. If you want to do it in just one piece, then do it that way. Okay? So you should go through all of this and make sure that you're right. Do the integration as an exercise, the double integration as an exercise. Make sure you can set up the regions, and make sure you can set up the bounds of the integration properly. Go through that, and you should get that the probability is the probability is 1/2. Okay. All right then. I'll see you next week.